Now on to processing data for geological modeling. So this is basically pre-processing some of our data so that they can be used in various modeler classes for generating our models. So these are producing the inputs, not necessarily our hard inputs like manually digitized points or polylines, but more data extracted from drilling itself. So the first one we're going to deal with is how to extract contacts from interval data. So in the first example, what we'll do is we will extract the contact between, say, our overburden and all underlying lithotypes, and this can be used, in subsequent processes to model surfaces and that sort of thing. So let's just make a variable contacts, and then what we'll do is we had our data already loaded, so we can use our get contacts, and we will use the variable, define the variable rock type. Okay, and the category of interest that we are actually after is number 5. If you remember back up to the 3D view that we looked at, because it's contacting all contacts, all other lithologies, we don't actually have to worry about, in this case, of defining an outside category. We just define it as category 5, and then we want to define what the contact type is. So in this case, we only want the footwall, so that's abbreviated as FW. If we only wanted the hanging wall of a rock type, it would be HW, and if we wanted to extract both hanging wall and footwalls, then we would say both. Okay. If you want to look at what other options there are, there's an orient argument. So orient basically means the footwall is being defined relative to this orient. So in this case, the plane is XY, so the footwall is the last contact it is going to find. We're keeping outside, meaning that if it finds various overburden contacts contacting different lithologies, it's only going to keep the last one. And then include ends is set to false. So this is basically if we have this particular rock type at the end of a hole, if we had that as true, it would make a contact there. Okay, so then we can just preview this and have a look at what the data frame would look like. Okay, so there we have it. We've got our drill hole ID where that contact came from, the XYZ coordinates, the depth down hole where that contact was found, and HW footwall, whether it was the hanging wall or the footwall. Okay, and then we could go ahead and visualize this. So let's just load our drilling again, and then we go v.add our contacts. Let's give them a bigger point size. Equals 20, say, and let's have a look at what that looks like. Okay, so there's our contacts. You can see these guys there, and they've all plotting at the contact between our overburden and all the other rock types. Okay, in our example 2, we want to extract multiple contacts along a drilling trace. So say you've got a unit which is going in and out, then you might want to extract a whole bunch of contacts down that. So let's go ahead and do that. Okay, so contacts equals data.get contacts again. And now let's say, okay, we define that rock type again. And in this particular case, we will we'll pick rock type 0 and 2 is our inside categories. Okay, so 0 and 2 is basically this one and this one. Sorry, we'll pick rock type 1, which is this one, as our inside category, and our outside categories will be the green and the blue one. Let's do that. Okay, so the inside category is 1, the outside category, so we're defining which one we want it to contact. So the 0, which is the orange, and we're also we're lumping the vein, which is the red, into this grouping, so that it's wherever either of these contact that green or the blue. And then in this case, the contact type we will define will be both, meaning that we're going to extract wherever it's contacting these, not just one per hole. So if we look at this, we can see now that we have both hanging walls and footwalls being defined. You can see multiple intersections per hole. Okay, and if we want to visualize that, we can simply go ahead and visualize this, and now we can see that we've got these multiple intersections, and I've flagged them by hanging wall and footwall, coloring them by that, so we can see that we've got these different intersections that have been flagged. Okay, now a more complex one. Okay, this occurs quite common in structurally complex deposits. So for example, you've got a fold that's folding over on itself, and holes are intersecting a body twice. So it goes in, goes out again, and then into that again. And the actual the limb of the fold, the fold is folded over itself, so the inside of the fold actually sits overturned. Okay. So what I've done here is I've just created a little fictitious little fold, and we can have a look to see what that looks like. So we have these two planes. It's green on the one side, red on the other side, showing you what their inside and outside directions look like. You've got these arrows pointing, which showing their vectors. They're pointing at each other, and then we've got these intervals here belonging to the same vein, but it's folded and come back on itself. So we're going to use these two planes, which are pointing at each other, as a reference surface, and we're going to use them to define which is the hanging wall and footwall of these veins. Okay, so let's go ahead and do that. Okay, so we say contacts again equals data.get contacts. Okay, and in this particular case, I've called this field vein. Okay, so I'll just give them that vein, and then my inside category is going to be 1. My outside category, I don't really have to define it because they're all 0 or nothing. 1, 0 is nothing. And then the contact type will be both again, like we did in the example above. And in this case, we want to use the function not keep outside, but we actually want to keep all. Okay. And what we're doing there is we said if we selected only outside, we would only select one intercept and another intercept. Okay. But now it's not going to know that if we don't specify, okay, it's not going to know that this is an overturned fold. And it might just say hanging wall, footwall, hanging wall, footwall, right? But we want to tell it that this is an overturned fold by using these two planes which are facing each other. Okay, so then we say orient will be equals our reference. Our reference is basically these planes. If we look back up here, this is the object called reference. Okay, and then we can have a look at what our result looks like. And we know we have this hang wall, footwall things happening again. But if we plot this up, we're going to see something different here. Okay, so now we see that these contacts, it goes, if we look at the coloring, so it goes hanging wall, footwall, hanging wall. So basically telling it that this is a vein that's folded over on itself. So then if we were to use this to build a vein, it would correctly fold the surface back. Obviously, doing vein modeling at that point, you would need to use this reference surface as well. Okay. Moving on to signed distances. Okay. So what are signed distances? So signed distances are basically a distance which has been calculated between points inside and outside of particular categories. Okay. And what their distances really represent is a distance to a contact between two different rock types. In RMSP, negative values represent inside the volume, while positive values represent outside values. We have a class called RMSP.geology signed distance, and in that class we have various different methods. There's the calculate cats, there's the calculate cats all, and there's the calculate cats by pair. The one that we will use most commonly will be the calculate cats. Okay. First thing I'm going to do is, and you'll see why I'm going to do this in a bit, but I'm going to define the variable that we're going to use. So which column in the database. Okay. And then first thing we will do is we will initiate the class. Okay. So geo.signed distance. Okay. So there we've initiated our class. Okay. And then what we could do is we could calculate some SDF data by using the calculate cats. So if we do calculate cats, okay. So now it functions the arguments are very similar to the get context arguments. So here we're going to provide our data. Okay. We could provide point data, but in this case, we're providing interval data. If you provide point data, it cannot calculate a signed distance at a contact. If you provide interval data, it can calculate those signed distances at the contact. Okay, so our inside category, in this particular example, say we can give it inside categories 1, 3. So that was that skarn and that vein unit. And then our outside categories, we could do that basement lithology and the overlying lithology, which predates the skarn. Okay. So then one thing that we'll right off the bat is we can have a look at the length of this data. So we can say length of data, and let's just say len SDF data, and then we can also look at what this data looks like. Okay. Oops, I seem to have made a mistake somewhere. I have forgotten the variable. After defining the variable so diligently, there we go. Okay. So if we look at the length of the day, it's 24,274. For our dense and sparse solvers, that will take a couple of minutes to solve. For our fast multiple solver, that will be seconds or milliseconds to solve. And we'll talk about what we can do about actually removing redundant data in a second. Okay. And then we can visualize this by cutting a section plot through this data and see what this looks like. Okay. So here we have, you can see why I created that variable before, because the actual variable that it outputs adds this prefix to it. So I've recorded that variable there so I can use it for downstream use. Okay, but now we're looking at a cross section through our data, and we can see that these negative values on the inside of the rock type of interest and the positive values are on the outside, and the white values are near the contact. And we actually, in this case, actually have contact points, so SDF values equal to 0. Okay, so as I mentioned, that's over 20,000 data. And for the fast multiple, this is a problem, but our density sparse solvers, it becomes more inefficient. So what we can actually do is we can reduce the amount of data that we need. So there is a decimate methodology. And what I'm going to do now is just demonstrate what that decimation actually does. Okay. So if we go back to our SDF class, we have a decimate function, and then we can provide our SDF data. Our data. And then we have to provide a variable, and then we can just copy that variable from here. And if we look at the arguments for decimate, it's asking for decimation factor. So this means that it's targeting 50% decimation, although it may not strictly reach that target because it will always retain data near contacts and data at the end of holes. If we raise that to say 0.9, that would mean it would be targeting a 90% reduction. If we went to 0.1, it would be targeting a 10% reduction in the data. So if I just go to the default, which is 0.5, what we'll see is that it's outputting a bunch of trues and falses. So these we can use as a mask. And then we could say, we could go like a length SDF data. And then we would see that we're down to 11,000 data. So we've reduced the amount of data. But I think it's actually pretty useful to see the impact of the of different decimation and what that looks like visually. So I've pre-prepared a little loop where I'm looping through a whole bunch of different factors, and then I can run through that and we can see the output. Okay, so here we can see we've got 24,000 data at a 0 decimation. I drop down to 0.1, it's 20,000, 0.3, 16, 11,000, 9,000 at 0.6, and then at 90% reduction, we're down at 2,400 data. What you'll notice is that we still have information around the contacts, even at 0.9, but probably the decimation at that point is a little bit excessive and may start impacting your shape. You may find, and it's something that you can test, is that there's little difference between the output volumes using a 0 decimation or 0.3 decimation, or even maybe up to a 0.5 decimation. Okay, so now we'll talk a little bit about our structural data and our structural plane data object that we have. So it's a useful data type in RMSP, and you can use it for things like structural analysis, plot them on stereo nets, estimation of locally varying angles, so LVA fields that you can use in downstream modeling purposes, to generate offset points, which can be used as a guide or an input into geological modeling. You can use these structural data as direct inputs in geological modeling, and there are different options for how we are treating their orientations, the ups and downs, whether they're on the surface, off the surface, whether they impact the magnitude of the values or not. So there's lots of options. And then structural plane data can be derived from many sources, including raw, alpha, beta angles, from dip direction, from extracting from your mesh triangulations. If you have existing normals, you can generate the structural plane data from normals. It'll estimate structural plane data from points scattered in space. You can get it from polylines, and then like we did earlier, using the from struct dip. The most common way would likely be from raw data, alpha, beta, or structural measurements, struck and dip. So in the following example, we're just going to quickly show you how you can generate some structural data from some points. So let's just first I've got some pre-written code here where I'm going to just show some points in space. Okay, so we have a bunch of points, and if I just take the static view off of this, we can see that they represent a contact or something like that. So that's the contact for rock type 1. Okay. And we can see we've got these points in space. Okay. So what we simply do to estimate the structural data, which is pretty simple, we can just go like struct dat or something like that equals RMSP dot structural plane data from points, and then just provide those contacts. And then we can view these. Well, let's just have a look at what it's done first. And we see it's created some structural data for us. Okay. There's a whole lot of other options which are related to this. So if you're finding that the disks which are coming out of your structural data are not quite as expected, there are other options to actually sort of refine the angles coming out. Okay. So now we've got this structured data, and we can simply view it in 3D. And so let's view it in 3D. What I'll do is I'll just make my radius, say, equals 5, and my thickness, equals 2. And there we have our structural data, which has been estimated from the points. It's done a pretty good job. Sometimes what you will struggle with is that it will not do a good job where you have clusters of data. If you want to deal with those clusters of data, you can always use the RMSP dot decimate uniform, which will then sort of decluster some of the points and get you better structural measurements. From these structural points, we can generate some offset points. So offset points are essentially 3 points generated per structural plane, and one will be at the center of the plane, at the XYZ of that structural plane. And then you can have one or more points then projected perpendicular to the plane along the normal, and you can specify what these offsets are. And then you would do the same thing in the negative direction. When you use large offsets, you may get conflicting offsets, and this is dealt with in the background in RMSP. So let's create some offset points. So that struct dat which is created dot get offset points, and then if we look at the arguments, we have the columns. That'll be the item column, and then the offset. Okay, so if I just say 5, if I just give it one number, And I have a look at the offset points that had. Oops. You can see it's, let me just maybe show a little bit more, 10 records. So we've only got -505, okay. But say I wanted to add more, I could go 1,5,10 or something like that. And then you'll see we have -10, -5, 1, 0, 1, 5, 10. Okay. So let's have a look at what those look like in the scene. So if we go V equals offset points view 3D, and let's look at, we want to look at that. The SDF is the variable we want to look at. I normally use, for this type of data, I'll use a blue, white, red color map, because then I see the white is at the contact, and I would normally give it symmetric limits, although actually in this particular example it wouldn't matter because the offset points generally are going to be symmetrical. We could add our topo and give that an alpha, and then have a look at that. Okay, so now you can see it's created a whole lot of offset points perpendicular to those structural data, and this can be used directly in your surface modeling to create surface from these points. So very, very useful as an auxiliary data type to be used in modeling. Okay, so that is processing in the data. If we want to look what we could actually do with these, we could sort of quickly just make a mesh out of these points. So I've just initialized the surface modeler. I've added these offset points. The ISO level is the field that I'm showing over there. And then I've just set a quick grid there. And then I could always view this just to give you an idea. So I've got all these terribly large points that are created, and there's the surface created from those points, and you can see it lines up pretty nicely with the structural data, although the surface is actually created from those points. Alternatively, we could also create the surface. Instead of adding the offset points, we could add the structural data, and if we just initialize that and have a look at that, I'm just going to take static off here. There you see our surface generated directly from the structural data. So almost identical to what we just saw up there. And that is the end of our processing section, and should give you some good guidance on how to process data prior to geological modeling.